This time we're going to look at numbering systems and how we deal with numbers in computers. Okay. Previously on PLC, we looked at a problem with 3 pumps. We had these 3 pumps, pump X, pump Y, and pump Z. Hopefully some of you were here last week and saw that. Did you see that? Were you all here last week? Well, if you weren't, don't worry about it, because you can download the recorded version and watch it any time. Right, so we had a bunch of I/O, we had a bunch of inputs, and we had some outputs, and we were lighting some little indicator lights. And we had 2 little green, we had 1 red light which came on to tell us that pump X was in fault, and 2 little green lights which came on to tell us how many of the pumps were running. It was a thing called a status code. And one way or another, we came up with a relay solution like this. I'm not sure if you would have had a chance to go and play with an Allen Bradley yet, or go and play with a PLC and enter this sort of stuff, but if you have, that's great. If you haven't, it doesn't really matter. We also looked at the block solution. Now, the block solution we implemented using a simulated program, a simulated PLC program from Cruzet. There's plenty of PLC simulators out there which allow you to simulate function block programming. Before we go too much further, what I'd like to do is do the wiring for a memory circuit. Now, on a normal relay, when you energize a coil on a relay, it goes click, because the coil is an electromagnet and it pulls the metal contact over towards it. Then when you de-energize the relay goes click again. The reason it goes click is because there's a spring there which has pulled the contact back. Now, if I took the spring away, that flap would not move. In order to get it to open back up, we'd have to put a second coil in there. And that's the type of relay we use for a memory circuit. We have 1 coil which pulls the thing one way, and another coil which pulls the contactor another way. It's called a flip-flop. And you press it, you press the set button, and the contactor closes, and then you can let go of the set button, and the contactor stays closed. It's remembered to be closed. So we can use that as a memory circuit. Here is another type of memory circuit. Has anybody ever seen this type of circuit before? Well, where have you seen this circuit before? It's actually used for motor starting. It's a latching circuit. And once again, you press the button and the motor starts, and then you can let go of the button and the motor remembers to be started. So it's a memory, and it stays running until you press the forget button, at which point the motor stops running. So that's how we can make a memory circuit. Making memory circuits is relatively easy. What we can also do is we can replace these switches and relays. Now, I'm not an electronics person, I loathe electronics, but apparently you can replace switches and relays with transistors. So that would mean if we were to throw a few transistors at this thing, say 1, 2, 3, 4 transistors, we could make the transistor equivalent of this circuit. That would give us what's called a 1-bit memory location. To go from there to the 8 gigabyte memory stick I've got sitting on my desk, all it would mean is reproducing this circuit, say 64 billion times, which isn't a difficult thing, it's just a little bit time consuming. Now, to do anything really useful, we need to actually deal with real numbers. We need to deal with numbers, not just ons and offs, but 10s, 15s, 4 to 20 milliamps, 0 to 10 volts, 45 degrees C. We need to deal with real numbers. Now, the way I always like to explain real numbers is to use a thing called the number wheel. This is what a number wheel looks like. I'm sure you've seen them before on cars. It's the sort of thing, it's the odometer you use on your car to keep track of the distance. This type of number wheel uses base 10. There are 10 figures around the wheel. I've represented it here at the bottom as kind of like a wheel on its side. And there are 10 figures around the wheel, going from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there's 10 of them. The first wheel is the units column. The second wheel is the tens column. All of the numbers in this second wheel are worth tens. That's how much they're worth. And the third wheel is the hundreds column, and all the numbers in this wheel are worth hundreds. So using number wheels, 375 means 3 hundreds, 7 tens, and 5 units. Now, I'm sure you're used to this numbering system. It's a positional numbering system, and that gives it special qualities. By positional numbering, what I mean is each position is worth a different amount. This position is the units, this position is the tens, and this position is the hundreds. That's very different from, say, the Roman numbering system. In Roman numerals, this, for instance, stood for 4, but it shouldn't do. By rights, this should stand for 15, because we've got a 1 and a 5. So the Roman system was not a positional numbering system. Ours is positional numbering, and the position matters. The aim of this course, this evening's course, will be to design some circuits. Last week we designed the circuits for a pump monitoring system. This week I would like to design the circuits for the inside of a calculator. So that's my ultimate aim. Now, calculators are pretty dumb things. So in order to understand how a calculator works, we have to understand how sums work, and we have to understand how sums work in the same way as you were taught in pre-primary. So all the things I'm going to talk about, they might at times seem incredibly simple, but that's because I'm always going to be referencing back to pre-primary, because we have to work at that level so that a calculator can work. Okay, we have number wheels that are different. Not all number wheels have got 10 digits around them. Here is a set of number wheels. The first number wheel, this one over here, which I'm going to call seconds, just for the sake of argument, that's got 60 digits around it. So I say it's base 60. The next number wheel, which I'm calling minutes, has also got 60 seconds around it. So I'm calling that base 60 as well. The third number wheel, which I'm calling hours, has got 12 digits around it. So I'm saying that's base 12. Now with this number wheel, if I'm given a number 4, 35 and 14 seconds, I know that that's 4 hours, 35 minutes, and 14 seconds. What would the time be in 1/2 of an hour? Hello, nobody's answering yet. If it's 4:35 and 14, yep, in another half an hour on from 4:35 and 14 seconds, what will the time be? Okay, it'll be 5:05 and 14 seconds. Now, most of you, I'm sure all of you, can do that. What you're doing there is you're actually converting from one base to another. Half an hour is in base 10. Half is in base 10. So what you've done is you've taken the base 10 and you've used that to convert the base 12 number, which you've realized is actually half of an hour is half of the base 60 number, which is 30. You've added 30 to the base 60 number, and then it's gone round the end and ended up at the 5. And then this hour one was incremented by 1. Now, all I'm trying to show you is that you're actually very capable of working in different numbering systems. We're not stuck with working in base 10. We can work in lots of numbering systems. If I was to move on from here and carry on going in wheels, the next wheel I would have would be a very simple wheel that would say AM and PM. And this wheel would change over every 12 hours. What would the base be for the AM-PM wheel? Base 2. Base 2 is a special base. We call it binary. So it turns out that you've been working in binary for years now, ever since you learned how to tell the time. Which is good, because computers work in binary, and since we're so experienced at it, it's not going to be a problem. So this is a very, very simple wheel. It only has 2 digits on it. It's base 2. And we normally call these 2 digits 0 and 1. Now with this very simple wheel, it goes up. The first wheel is units. The first wheel is always units in all numbering systems. So the first wheel is units. That's worth onesies. The second wheel is twoses. Everything in this wheel is worth 2. It's the twoser column. The third wheel is the fourses. All the stuff in this wheel is worth 4. So if I have a number, a digital number, sorry, a binary number, 101, that means 1 fourser, no twosers, and a unit. So if I've got 1 fourses, no twosers, and a unit, how much have I got? Okay. This is obviously going very well for most of you. If I just draw your attention to the buttons at the top where you can tell me to speed up or slow down. If I'm going too slowly, just tell me to speed up. So we have these 2 numbering systems, which we're going to talk about a lot today. We have the decimal system, which uses hundreds, tens, and units. And each column is worth 10 times as much as the previous column. And we have the binary system, which uses base 2, and that goes up fourses, twosers, and units. Each column is 2 times as big as the previous one. When we look at this in numbers, what we get is in base 10, it goes up units, tens, hundreds, thousands, 10,000s, and 100,000s. Now, units is onesies, and that's 10 to the power of 0. The next column is tens, and that's tens, and that's 10 to the power of 1. The next column is 100, which is 10 times 10, 10 to the power of 2. The next column is 10 times that, so 10 to the power of 3, 10 to the power of 4, 10 to the power of 5. So, you see, if you want to know the value of any column in decimal, you just have to do 10 to the power of the column number, where the columns are numbered 0 through. So 10 to the column of 5, 10 to the power of 5, sorry, will be the size of the fifth column. Same with any other base. In base 2, which is binary, the first column is units, which is 2 to the power of 0. Anything to the power of 0 is always 1. The next column is 2 to the power of 1, which is 2. Then 2 times that, so it's 2 squared. Then 2 times that, 2 cubed. 2 times that, 2 to the power of 4. And 2 times that, 2 to the power of 5, which is 32. If you want to find out the biggest number you can store in, say, 5 columns, the biggest number you can store in 5 columns in decimal is 10 to the power of 5 for 5 columns minus 1, which would be 9999, 4 lots of 9. The biggest number you can store in 5 columns in binary would be 2 to the power of 5 minus 1. Now in binary that would be 1, 1, 1, 1, 1. Sorry, 1, 1, 1, 1, which is 32 in decimal. So, each column is twice the value of the one on the right. Here are the columns with their values above them in decimal. What I've got here is 8 columns, what we call an 8-bit word. If I have 8 columns and it's completely maxed out, I've got ones in all the columns, what's the biggest number that I can store in 8 columns? Actually, it's 1 less than 256, because 256 would be 1 more than what I've got on the board right now. So it's 1 less than 256, which is 255. I can store 256 numbers because of the fact that I'm also storing 0. So 0 to 255 gives me 256 numbers. So I can store the numbers 0 to 255. Now, these are positive whole numbers. There's no fractions and there's no negatives. There's a special word for whole numbers. I should have written it down. Whole numbers. They're called integers. Whole numbers are called integers. And it's a horrible word, but that's what they're called in mathematics, and that's what they're called in computers. So whenever we talk about integers, we're talking about whole numbers, no decimal places, no fractions. In this case, we've got positive integers. There's no negatives. Now let's just do a little bit of the naming of names. One binary digit, binary digit, binary digit, binary digit, they reduce that to bit. Binary digit sounds a bit like bit. And 8 of those binary digits, 8 bits, sounds a bit like byte. Now, because there were nerds involved, they said, well, what would half a byte be? Well, obviously a nibble. Very funny. 16 bits was called a word, 32 bits was called a double word. Actually, increasingly nowadays, we're just calling it a 16-bit word or a 32-bit word or even a 64-bit word. So rather than giving them their own little names, we're just saying how long they are.